So yes, I'm very glad to be invited to give this talk on muon GMAS 2. So this one will be mostly on experimental setup and results. So let me go strictly to our collaboration. So this is a international collaborative work, and we have 7 countries and 35 institutions, and over 100 collaborators. And this is my institution. And then maybe a few pedagogical background about the G-2, why that is interesting. First, this is actually one of the most fundamental properties of any particle, charged particle, because it has a spin. It relates from its spin s and its magnetic momentum, right, like illustrated there. And for the classic system, G is equal to 1. And then for any particles such as electrons and muons and stuff, it should be 2. I will explain in the next slides why it's 2. And then for composite particles, it's not to 2, but what is exact number is actually up to people to find out. For example, the proton is 5.6, and neutron doesn't have any charge, but it has G equal to negative. So it's kind of intriguing, and it provides a unique perspective to analyze the particles without breaking it. And then y is 2 is actually from this famous direct equation. You get it directly from there. So this is theory prediction, right? Our experiment is interested to see why, how it is exactly due to or any difference. So actually, starting from 1948, people were starting to measure these G factors, starting from the electrons. And then we measured at LHC-1, and it's 0.1% deviation from the theory prediction. And people are interested to see, where does it come from? Why it's different. And it turned out that the space, it's never empty. There's virtual particles popping in and out and do this so-called radiative corrections. So I'm assuming most people know this and in this conference, so I'll go very quickly in this background thing. But this is important to notice that the Schwinger is the first one to calculate this first order calculations. And this is from most textbook, you already see this. And then for the experiment, you get this. So it's very interesting to see that, this is the history of the GMAS2, right? The theory improves, the experiment improves, and they're not quite matched. They're always a small difference, right? So this is the tone or the general idea of this precise measurements. It's very precise, and there's always a difference between the experiments and theory. And then this drives us to the first order QED corrections and the foundation of the standard model. And that's why Julian Swinger put this on his tomb, right? So it's lifetime achievement. And then it's natural to think maybe there's high order corrections. Indeed, there are more quantum corrections. There's electric corrections, there are hadronic corrections, right? I'll just go through them quickly. And then there's some unknown corrections even, right? Something you haven't think about. And there's difference always there in the theory and experiment values. And you can see even at this 10, 11 digits, there's a difference there. And then that's why this is interesting, because we want to explore the new physics beyond the known physics, right? So that's why GMAS2 is interesting. That's why we want people who want to measure it, right? It's because it's sensitive to new physics. So I'm not a theorist, so I just steal one slide from a theory people. This is actually given by this GMAS2 theory initiative in their summary report from last year. And then it nicely summarized all the corrections I talked about: the QED weak, hadronic, vacuum polarization, and light by light. And you can see the corrections goes dramatically smaller when you go to the hadronic one. However, the uncertainty actually becomes bigger, right? So actually, I think it's easy to understand, right? Because the correction is so small, that's why it's so hard to get it exactly right. So this was driven the theory, uncertainties, the hadronic corrections. And what about the experiment? The experiment also improves dramatically as well. It's starting from the NIMS, from the CERN experiment, and then to the BNL, and then finally the Fermilab. You can see how much the error bar shrinks, right? And this is all of the corrections we can probe to, right? So it goes to really to the sub ppm level now, right? So in BNL analysis like 0.5, and what we expect for this one is new experiment is 0.1. We're not quite there yet, this first result, but we already exceed the BNL sensitivity. So that's very promising. And this is the level of citations we have, right? We're catching up quickly. I haven't updated this citations since, I don't know, since summer or something. So it must increase bigger than that. And then the comparison, we want to compare theory and experiment. So maybe take this one example. It's just different in theory curves. So there are different theory, HVP corrections, and then these are the three leading ones, right, which has a smaller uncertainties. And then this is the previous one, the BNL experiment. You can see there's a large gap between these two, right? And it turns out this is zoom in thing, right? It has large gap there, right? But there's also a lattice QCD calculation, which actually covers both the standard model and the existing ones. But this, the lattice one has large uncertainty, so mostly we still focus on the, the standard traditional ones. There's new calculations, but the theory people are still checking it and verify it. So we still take this one as our, world average value of the standard model ones. We do not pick which one to compare, right? We just take the consensus from the theory community. The recent lattice QCD by BMW group, you probably all know about it. It actually, I think it's somewhere here, yes, right there, right? It has smaller uncertainty and is closer to the measurement. But I just quote our theory friends, it needs further study, right? So, but that's not the center of my talk. Maybe the next theory expert will talk about that. For me, I will just focus on the experimental results. So this is our experiment results. I'll just give you right there, assuming most of you or some of you already know this. So this is a standard model, and this is the experimental results, and this is this talk, and this is from like 20 years ago from the VNL. It's amazing that they actually agree quite well, right? I think this actually gave us, confidence that, our measurements, it's solid. And if you combine these two and then compare with theory, the ones I explained in the previous slides, you will see that the difference is huge. It's 4.2. It's even bigger than the 20 years ago, right? Because we improved the uncertainty, right? So this is strong evidence for beyond standard model physics. And, I have to say, Susy is definitely still one of the most promising theory or motivation to explain this 4.2 sigma. Of course, there are many other new scenarios like dark matter or axion, right? Like can also explain this. I'm sure next speaker will probably talk more about this. All right, so enough with the introduction. So I will go to the experimental principles and methods and how we can make sure we got that 4.2 sigma. So how we do this, we actually measure from G-2 divided by 2, this is difference, right? We actually measure by using the frequency. So if you put a charge particle to the electric field, it will process, right? And it has this precession frequency. And then, if you go make it do rotation, it will also do the cyclotron frequency. So that's where we can take this two frequency and take a difference between these two. So this is the P, right? And this is a cyclotron frequency. And then the S is this precession frequency. And then you take this two and you get this one. So if this one is perfectly aligned, then you will see them always has the same difference between two, and then you measure nothing. However, there's a difference, then you always measure something. So this is why we can get this measurement from this frequency difference. And why we are so focused in frequency, this is nicely explained by 1941 Nobel laureate Arthur Schorlow, and said, never measure anything but frequency. Well, he's a laser guy, so he's probably biased, but still, and frequency is one of the best way to make precision measurement, right? That's how we can make things precise, because you just count things, right? It's easier to get a precision in that way. So that's why I want to do this, and then I'll just take the previous formula and translate it to a bunch of frequencies. So basically, the omega A and then omega P. Omega A is the precession, anomalous precession frequency I explained. And what about omega P? Well, omega P is actually proportional to the to the magnetic field. It's like the proton precession frequency, and you use that to measure the amplitude of the magnetic field. So you still write in this way, but you're actually measuring a field, right? And the rest of the just constants or better measurements from other experiments. So I will just leave there. You can check this one from this code data data book. And then the rest of it is fairly straightforward. You just put the muons into a ring with a magnetic field. But I have to stress it's uniform. It has to be uniform, because otherwise this denominator will become very complicated, right? You want it to be uniform as possible. And then you take the denominator and denominator and then divide by them together, right? And then you get your final answers. Of course, you want to do a blind analysis because you don't want to bias yourself. And then this is another way of doing this experiment. This is I borrowed it from a science education journal, and then this nice illustrated graph to tell you that you get protons, you hit a target, you use pions, and then you inject to this field, and then it goes circles, right? And then these muons will decay to electrons or positrons and hit our detectors, right? So this is the idea. And what is G-2 then? Is when this muon decay or about to decay, it could interact with this virtual particles. It could be virtual photon or virtual neutrino, or could be any new physics, right? And then it will slightly, nudge a little bit of this precession frequency, and then that will be detected by our detector. So that's the idea how we detect anomalies. Again, this is how the schematic, the setup is doing, and this is a real picture of the Fermilab. And this is where this experiment will be conducted, and this is where we're standing in front of it, and then this is where this ring is located. So this is the magnetic superconducting ring, which provides a uniform magnetic field. Okay, so I will probably skip this one. It's a little bit complicated to explain in a few minutes, so I will skip that. But basically it's the same. You just inject protons and get the muons in the end. And then there's the same thing. Again, maybe just leave with this picture. Then this muon will decay and this along this object, and then the electrons will hit the calorimeter in the end, and then go through the tracker in between, leave some traces for us to detect them. Okay, and then maybe a little bit more on how we make sure this injection goes to where we want it to be, because the muons go this way, it actually go straight line, right? You want to bend it towards inside this magnetic field, so you actually need an inflector, right, to help you to guide the muons to where you want it to be bend. You don't want it to bend randomly or too early or too late, right? You want it to bend exactly the moment it enters inside the ring. So that's why you need this inflector. So it actually has it's like a shield, right? It's superconducting itself. It provides the field-free region for muons to enter the ring. So inside here is actually magnetic field free, right? And then at the same time, you don't want to perturb the main precision field. So this is a very delicate device. And then once you're inside it, right, you put it in there, and then the beam will bend, right? It will bend inside. Then we need 3 kickers to make sure it don't go too inside, right? You don't want to hit the center or something. So actually the 3 kickers will move it, push it outside just a little, not too much, right? If it's doing too much, then you'll have big problem with a refractor. This kicker is just a nudge muons a little bit into the orbit, and it's very fast, right? Because you want to catch all these beams, in fast injection mode. So that's why you look at this time scale. It's like 0.1, 0.2 microseconds. So very short period, and then you kick it with the pulse magnet, strong field like 200 Gauss something, and then to nudge the beams into the center of the vacuum chamber. And then finally, you want electric quadruples to focus it. The reason for that is we only talk about the horizontal things, right? Bend inside or kick outside. This is all horizontal, parallel to the paper plane. But what about the things go, helix, right? Go viral, right? And then it will be not so good. So that's why we wanted this to be, vertical confinement. So that's why you still have this one to focus beam to go in the middle, right in the middle. So that's why it has electric quadruples to help you do that, and has power voltage there. Right. So this is the final schematics for the magnetic ring with all the components I talked about. And this is a real picture. So the same thing, you go to muons and you go inflecting inside, and then you go circles, right? And then this is the kickers, and these are the parts I talked about to focus, make the vertical beam focusing. And then you have 24 kilometers, and then you also have this NMR pose, which is inside, you cannot see it, right? It's inside of it just to monitor the magnetic field to make sure it stays stable and uniform. So let me go quickly to measuring this different magnetic field, right? So you have the omega A, the same thing I said before, it decays along this path, right? And then depending on the direction of your P, right, and your S, if your S and P aligned, then you'll be a very energetic electron decay products. If it's anti-aligned, then you will go backwards. But because you have a huge boost of the muon going forward, so you will just have a softer energy spectrum of the electron. So, right, but still you can make a threshold cut here, and then you will see some of the muons are aligned, some muons are anti-aligned, and somewhere in between. So this is actually explained in this cartoon, right? When it's aligned, you have an energetic one. When it's anti-aligned, you have a less energetic ones. And then you can use that. And that saying, that rotation frequency is the anonymous precession frequency. So you can actually use that to fit this formula, and then you can try to extract, oops, yeah, I go too fast. So you can extract this frequency. And this one, the peaks are the aligned ones, the bottom are the anti-aligned cases. So it goes like this, and then you circle it back, okay? So actually, it goes quite long, but it just circles back and forth. Just to make it better plotting. Okay, so we call it wiggle plots. So if you do this experiment, you fit it in the time and energy 2D spectrum, you will see something like this, right? And these are the oscillations I talked about, right? And then you will also notice there's something here. What about this, right? These are actually a background, right? And these, you can see that these actually are fairly constant, right? It's decreasing, but it doesn't have a very strong frequency dependence. At this one is because it's a lost muon, which means the muons are lost are detected without decaying. It just hit our detector. So these are the one actually we want to remove, but it's easy. You can just make an energy cut, right? We just cut out these ones. So after we clean up our quality, and then you have something like this, right? So these are the ones I explained in the previous slides. So, and this is how the one data set, the ones I'm going to present results based on. And then this is omega A, okay. And then let me quickly go to the omega P, and this is the magnetic field, right? It's 1.45 Tesla, and then it has different yokes to it. It has different poles. So the beams go inside this one, right? And then you have this phase shift yoke to provide the dipoles, and then the beams go in between. And then we have a lot of shimming techniques. We have passive shimming, we have active shimming, both to make sure the beams, the magnetic field are uniform, right? Okay, so, and then as I said, we use probe to make sure it stays uniform, right? And then we actually, these fixed ones outside, we have trolley to go inside, like this one, right? And then we we make it roll, inside can chamber when the beam is off, right? And then we monitor it. When beam is on, we keep monitoring it, and we do a time projection to make sure this, the field stays, stable. And then we'll do the absolute cross calibration of all the probes, right? There's like 500 of them. And this is our monitoring results. So this is before we do the shimming, you can see there is quite a variation. But after you do the shimming, it's tiny, right? And this is 2D map. This is what the BNL has, and this is what we had. This is what we had like 3 years ago. And we actually keep improving. So the real ones actually is even better. This is, this is what I took like 3 years ago. Even at that time, it's already 2 or 3 times better than BNL. Okay, and then let's go. I covered about omega A and omega P, and now let's go to the final measurement. So this is the same formula I explained before. And then you have this omega A and omega P. I didn't touch about this because this is only makes sense when you have the omega P measure, because you actually want a omega P measure and also convoluted with the muon, because you want the field, as the muon presents, right? When the muon is there, what kind of field it has? So it has to be convoluted together with muon distribution. Okay, so this is the final results. So before I show it, I just show how we got it there, right? I will show the final results later. And so this is omega A, I explained before, and this is omega P. You can see that actually this one is better than I showed from 3 years ago. And this one I haven't shown, right? This is the muon distribution I mentioned in previous slides. And this is how we measured. We actually measure from the tracker, because the tracker can give you the trace, of the muon decay products. We can back extrapolate it and get the position of the muon. And then you can see that actually the muon is slightly shifted towards outside of the ring, right? So it's not totally symmetric, right? This is due to the beam tuning and then the the kicker we have. So, but we have the measurement here. We can just combine all this and get the final measurement. Okay, so and then before I get to the final measurements, I just talk about all the corrections we have, right? So for example, I only talk about the horizontal ones, but I never talk about the vertical ones. So actually you have vertical corrections to your classic electrodynamics formulas. You can write it in this way, and these are ones I mentioned about, and these two actually I didn't talk because they're in the high order corrections. So we actually can do this. How we do this is we can actually first minimize this one, right? We choose a gamma, which is 3.09 GeV, and then this term will be minimized. It's still there, but it's much more reduced. And then we actually measure this one as well at the same time, to measure the dark term. And the reason for that is there's a coherent Bhattacharya oscillations, right, which provides the beam will actually move in different directions, and we have to correct for that. So these are the the high order corrections, and these are the electric field and pitch corrections there. So why we worry about that? Because there is a coherent Bhattacharya oscillation. So this is better explained in this cartoon, right? So this is how the beam moves, real, right? So this is the beam position, radial position, and vertical position. You can see actually beam is not stable, right? It's fluid like, right? So, and this is also detected, by our detectors. And you can see actually it also moves, right? So that's why it's a beating effects, has both radial and vertical frequencies. So we have to actually consider that. But as I said, we have tracker to help us to get a location of that thing. So this is the mean position, and this is the radial position, and this is how we get its value there. So we can actually model that one and then put it inside. So this is E field corrections. I do not have time for this, so I will just probably skip that. So basically, you have to say that the details are in this paper. So this is high order corrections, and this is one of the many high order corrections we measure in our experiment. So there's pi up, there's gain correction, there's the CPU, and then there's muon loss, and then there's E field and pitch corrections. And then they are all there. So you can see this formula becomes very complicated there. And then this is how we improve. This is 5 parameter, and then this is 22 parameters. So you can see after all the corrections, this is a residual pull. The pull becomes much smaller and then flat. So this improves our measurements. And then we also have Fourier transform spectrum to see different effects there. And then after corrections, you can see it becomes flat as well. Okay, so I think I'm very close to presenting final results. And this is the systematics. Again, there's many systematics. We consider different measurements. This is the numerator, all the frequencies, and you can see there's uncertainties there. And then there's denominator about the magnetic field. Okay, and then the final results is what I showed in the beginning of the slides. And then we have like 3.3 sigma from the standard model. And these are final uncertainties. I think this is also very important. You can see that this is dominated by the statistics, right? So this is like a 0.43 ppm, right? So it's largely statistically dominated, and it has good agreement between 2 experiments, and it has smaller error than BNL. Okay, so why we can measure so precise, right? I just quickly go this because we have large statistics, and we have a uniform stable magnetic field, and we have a precision beam monitoring, and then we understand most of the background. Okay, if it's not physics, what else? Static fluctuation, experimental bias is unlike because there are many consistent checks, right? And then we'll have an important cross-check at the JPark GMS2 in next several years. And it could be theory calculations. Well, this is totally on the theory part. I think they are doing important consistency check for the HV calculations. I think they will sort out very soon. It could possibly both are wrong, right? There's small chance, but then we'll have to check with external evaluations, right? There's an interesting paper about the muonium hyperfine switching extraction, and then there's the electron GMS2, and people are even thinking about the whole GMS2, right? So we have to check them, but so far we haven't seen evidence that something is wrong. Okay, I will skip that. So this is blind analysis. And then there's one of the many cross checks we did. So this is from our SJTU. And then we checked every consistent, methods, look at the blue line, they all agrees. Okay, and finally, let's go to the outlook. So we have this 1-1 results using this tiny 6% of the data, right? And run 2 and 3 will come out soon. And run 4 is going to get like 13 times, BNL 3 times bigger than what we have at the 1, 2, 3, and run 5 go to 20, and then just recently, right? Just actually, last week, right? November 14th, we have run 5 going. So this is our run 5 data right now. So the conclusion is, right? This is first measurement is done with 4.46 ppm, right? And we have consistent results with BNL. And it goes to 4.2 sigma, and then we expect 5 to 2 improvement when we combine 2, 3, and then from 4, 5. So stay tuned. Once we have this one, and we have potential to reach to a 5 sigma when we combine all these. So thank you very much. Sorry for taking a lot of time here.
No, you are perfectly on time. Thank you very much for a very informative talk, and we can take a few questions. So First, I will unmute Rohini. Rohini.
Yeah, thank you very much. So really, I would like to thank you for a very clear talk and trying to explain all the intricacies. Now, can we go back to, where you talk about the magic momentum so that this higher order correction can be minimized?
Correct.
I had a question there.
Yes, let me go back to there.
I don't remember the slide number, but this was that gamma square minus 1. Exactly.
Yeah, this one.
Now, what I want to know here is that when you say choose gamma, that means that you choose momentum, select the muons from which, I'm confused how that is done, because finally we only detect the electrons, right?
Right, correct. So actually we do momentum selection when we generate these muons. So the muons generated by doing the target, right? You go proton hit the target to get a pion. So actually you already get it, when you do.
Oh, so you velocity, pre-select velocity. Okay.
Yes, correct.
Okay, thanks. And then I had one more smallish question, if you don't mind, not about G-2 of the muon, but the G-2 of the electron.
Sure.
The measurement for the G-2 of the electron, I think it's not as accurate as the muon, right?
Well, actually, it's much better precision than the muon, actually.
Then why is it so? I mean, here I thought this additional idea of getting the spin of the muon from, the angular distribution of the electron is very sweet. In the case of electron, how do you do the measurement of the spin direction?
So the electron actually get much better precision than the muon, but the trick there is it's not exactly a direct measurement. It's actually a measurement of the atom or molecular state, right? It's checking the electron's states, right, within a much larger a compound state. It's usually like a high Z atom state, and then you check how the muons change, right, in their excited states, and then you measure the G-2 there. So yes,
so it's more from the energy differences, is it? So there the thing is more from the energy differences that you measure of the states for the electron.
Yes, it actually use it also. Well, the one thing common is there. I'm not expert there, so probably you guys should invite another electron G-2 expert to explain that. But from my understanding is they also use the frequency techniques, but it's a different thing. It doesn't involve using this story ring technique. It's totally different thing. Yeah.
Okay. No, thanks for this very clear answer. Thank you.
Yeah.
Is there any other question?
Yeah, can I ask a question?
Yes, please.
Yeah, so this is Sudeshna Banerjee from TIFR. So my question is about the systematic uncertainties. So can you go back to that page where you showed the list of systematics?
Sure. I think I have it there. You want which one? You want omega A or omega P?
This one. Yeah, this one. So here, I mean, as we see that the statistical uncertainty is anyway very, very small. You have a lot of data now, but the dominant systematic uncertainty is related to alignment. Am I
right? Which one? Alignment?
The tracker.
You're talking. Yeah. Okay. Yeah. So actually, this one is actually not the dominant one. So actually, the dominant ones is actually here. This the omega A ones. So this is actually one of the component. So it said CP, right? So it's a pitch correction. So it's one of the corrections, right? So why this one is tracker dominant is because that one, that particular correction is very sensitive to the vertical position of the beam, and we measure beam position using tracker. So that's why this one is dominant, right? So, but if you're really interested to be the dominant position for the omega A is actually in this table. Yeah, sorry, there are so many numbers there. So, and then you look at these ones, you will see that actually the dominant one is still the CBO and then the pi up. So these are the two dominant source for getting the.
What do you mean by pi up here?
Pi up is when you have two electrons hitting our detector at the same time.
Okay.
Right.
So you can't resolve. I mean, so basically, it is the resolution between the two electrons that is hampering the calculation.
Right. It's fundamentally is because there is a high weight, very high weight of the electrons hitting our detector. Yeah. But we can use data-driven methods to correct for that.
Okay. And that is because of the beam intensity, or what is it related to?
Right. It's mostly beam intensity. Correct.
Okay. All right. Thanks.
Okay. Thank you very much, Professor Lee.